Hi, so this is going to be just a quick video on sort of a detail that I wanted to show you, and that is how to integrate area in spherical coordinates. So now that we're working with Gauss's law, um, that connects the flux, electric flux, through a closed surface to the charge enclosed by that surface, and what I want to focus on is, so we're going to work with lots of spherically symmetrical situations. So the simplest being like if you have just a point charge. And what you do is you choose a sphere as your Gaussian surface. And this has some advantages. So the electric field and the area vector for every point in that sphere are going to be aligned. So that dot product, in other words, that angle is 0, and so that dot product just becomes E dA. And then additionally, since this thing is spherical, for every r, the value of the magnitude of the electric field is going to be the same. So what that means is that it's constant, so we can pull it out of the integral. So this becomes E times this integral over the area. And what I wanted to focus on is we're accustomed to is this object. We're accustomed to just saying, oh, this is the area. But I wanted to show you what that looks like in spherical coordinates. So let me pull up this diagram. So this shows you the area and volume elements, differential volume element in spherical coordinates. And the part that I want us to pay attention to is if you want to find the area, so in other words, if you want to integrate over this area, what is that actually? Well, in spherical coordinates, notice here you'd have two contributions. So we're not changing r would stay the same, but we have two contributions. We'll have an r d phi piece, so that would be this piece. And then you also have this piece, and that's our r sine phi d theta. D theta. And this sine phi, you can think of that as accounting for the fact that these lines get closer together as you go to the pole. So, and these integrals, in order for this to be over the entire surface, we'd have to integrate phi from 0 to pi, from pole to pole. And then we would have to integrate theta all the way around. So this would be from 0 to 2 pi. And so what is this? Well, we can notice that r does not depend on theta or phi, so we can pull that out of the integral. And notice also that theta, well, actually, I'll do it in two steps here. So then we're just left with this sine phi d phi d theta. So we could, for example, integrate the theta piece first. That's easy. So that'll just be, notice there's no theta dependence in here. So we would just pick up squared. We would just pick up theta evaluated from 0 to 2 pi. In other words, we just pick up a factor of 2 pi. And then our phi integral, so what would that become? Well, if we integrate sine phi, that's negative cosine phi from 0 to pi. So this becomes 2 pi r squared. Cosine of pi would be -1, but that's negative already, so 1 minus negative cosine of 0 would be 1, so minus -1, so this becomes +1. So in other words, 2 4 pi r squared, the area, but explicitly done by integrating the differential area element in spherical coordinates. So hopefully this just makes gives you kind of all the detail about how this is actually an integral.